I'm going to be solving the heat equation with homogeneous boundary conditions, and our problem is this, the heat equation with boundary conditions equal to 0 and initial condition equal to f of x. And x is within 0 to L. Alright, so we're going to start off by applying the Laplace transform. Which is this. So applying this to our heat equation for WT, we get S W hat, the initial condition, and K W hat XX equals 0, where our W hat is the Laplace transform in respect to T. All right, and now we just shift some things over and divide by K, and we end up getting, so moving WXX to the other side, we get this, and here we plug in f of x for our initial condition, and then we divide, and then there's a k right here, and then we divide over by k, and this gives us where, this is a plus, where our lambda is equal to negative s over k. All right, now here we transform this into the Green's function, since this is, we can recognize this as an SL eigenvalue problem with an inhomogeneous eigenvalue problem. So we take the Green's function, deal with the inhomogeneous part, and we get and then our boundary conditions stay the same for the Green's functions. All right. And so just looking at the homogeneous version of this Green's function, we have, which is an SL eigenvalue problem that we've solved many times before, and the solution is a complete set of sums such. So here our G, since it is a complete set, our G will look like this. Now to solve for the coefficients a of n, we plug G back into our ODE to begin with. And so plugging it back in, we take the double derivative in respect to x, which will give us n pi over L squared out in front, and we take the derivative of sine twice, which will give us negative sine, plus this part of it, now we multiply both sides by sine of m pi, so I'll write this out. But you multiply both sides by sine of m pi over L squared and integrate from x equals 0 to L. And so we multiply both sides, and due to the orthogonality of the sine functions, everything will go to 0 except for when m equals n, and so this effectively removes the sum part of this, and so we're left with 0 to L sine squared plus lambda 0 to L sine squared, and then the other side we just have the delta function multiplied by sine. Oops. Okay. Now we can recognize that the integrals of these of sine squared from 0 to L turn into L over 2, and so we have a of n L of 2 multiplied by lambda minus n pi over L squared. And then the other side, the identity of the delta function, it just becomes a shift, and so it becomes sine of n pi x naught, because the delta function is only non-zero when x is equal to x naught, and then that just leaves us with n pi x naught over L. Okay, and then we solve for our coefficient, just moving everything to the other side. That. And so we can plug this back in, plug this back into our g function, our Green's function, and that gives us 2 over L 1 multiplied by sine n pi x naught over L, and then multiplied by sine n pi x over L. Yes. Now to go from G back to W naught, W hat, we take the convolution of G with the inhomogeneous part of this, and so we get W hat XS. So now we're getting our S part of it back. D of X naught, which is equal to, we plug this in. So right here, we can, I'll write it out. So we have 2 over L, n equals 1 over pi squared. And then multiplied by negative 1 over k f x naught dx naught. So this integral right here, in respect to x naught, there's only this variable and this variable that is in terms of x naught. So we're just going to take that out because that is going to remain relatively unchanged for most of this problem. So we end up just having a of n x naught 1 over, and we're going to multiply this 1 over k over here, and since this was originally s over k, we end up just getting s plus k n pi l squared. Yeah. And then sine n pi x over L. So here, our A of n is just the integral containing everything that has x naught in it. Everything outside of it would remain constant, and that's why we can take it out of the integral. All right. So here, all right, we apply the inverse transform. So apply Laplace inverse. And the inverse is given as, so to get our original function back, we take the integral from c minus I infinity to c plus I infinity of w hat times e of st ds. So this will give us, just plug in our w hat into this formula. All right, and an stays the same as before. So now we apply the residue theorem in order to solve this integral right here. So what residue theorem tells us is that this integral is equal to 2 pi I of the residue of each pole of S, where the residue is the limit as z goes to that pole. Z. All right, so applying this to, we want to apply this to solve this portion of our problem. And so we have c minus I to infinity, c plus I to infinity, sine n pi x over L. Now we can see that we have a pole when s is equal to negative of this, because then the denominator will equal 0. So our residue, or our solution with the residue would be 2 pi I times the limit as s goes to negative kn squared pi squared over L squared, multiplied by s plus kn squared pi squared over L squared, multiplied by our entire function. With e to the st. All right, now as s goes to this value, first off, these two cancel out. And then as s goes to this value, we end up just having 2 pi I times sine n pi x over L e to the negative kn squared pi squared over L squared t. Yeah. So plugging this back into our integral, we get that wxt is equal to the sum. And here the 2 pi I cancels out with the 1 over 2 pi I. And our our AN. Then our residue. Where our AN has stayed the same. This is interval. And that's it. We have obtained W for our heat equation.